Take a look around you and you'll find that everything is experiencing some form of motion. Whether that motion is an apple snapping from its stem and falling from a tree, or a cat waiting for the moment just before suddenly lunging at a bird, or a bird nimbly dodging a killing strike. We've been taught to describe enough to give another person an idea of what we see and even what we feel. But as physicists, we are interested in descriptions that give us insight into how things are, why things are, and why they change. So, how do we describe motion with that purpose in mind? Let's start with describing an object's location. Like this bird. Where's this bird? Well, it's sort of difficult to describe its location without a reference point. So how can we describe where this bird is in relation to you? It'd be easy if this bird were standing on a ruler or some kind of gridded map that would tell us exactly where it is in relation to you. So let's imagine that there is a grid that this bird is standing on. Let's imagine there's a ruler placed on the floor. Now it's easy. We can describe the bird's position. The bird's position is 3 meters from you. The 3 indicates size or magnitude of the quantity, and the meters indicates the unit of measurement. And the statement away from you indicates a reference point. But even this description can yield a number of possible locations. So to accurately describe an object's position, we need to include direction, such as north, east, south, and west. In this case, the bird is to the east of you. In physics, we often come across descriptors or quantities, such as position, that require a direction. We call these vectors. And because they require a direction, we represent them with an arrow. Cool. The bird's position is 3 meters to the east of you. But wait, we just described this vector quantity of position in relation to your position. What if you move? Well, that would change the position, or at least our description of position. That grid we drew, it's not really there. It doesn't exist. We use it for our convenience, which means our description of position is relative. There you have it. Position is a vector quantity that describes an object's motion relative to some point you choose. And it's measured in the standard scientific unit of meters. Great. Oh, and for future reference, let's give position a symbol X, because X marks the spot of something's position, of course. Now that we can describe where an object is, we can describe how that location can change. How far did the snail move? Let's put down our imaginary grid. It looks like the snail moved 6 centimeters. What you described is the distance the snail traveled. Notice how little regard distance has for direction. It's simply how far did the snail go, not where did the snail go. That's why we have another word to describe how far and where the snail went. Displacement. The snail's displacement is 6 centimeters to the right. To describe where it went, we need to include a direction, such as up, down, left, right. Because it has magnitude, or size, and direction, displacement is a vector quantity. If displacement is a vector, what does that make distance? We can say distance is a scalar quantity, meaning it only tells us how much, magnitude, and not direction. Let's go back to our description of displacement, the vector quantity. The snail was displaced 6 centimeters to the right. Wait, but your friend on the other side says it moved 6 centimeters to the left. Who's right here? Well, you both are. Direction is completely relative to the observer. Imagine you lie down on your side and you watch this snail. The snail would have appeared to move up 6 centimeters. Yeah, we physicists tend to think of things beyond absolute direction. Because, well, if you're in space, what's up and what's down anyway? So distance and displacement both describe how far an object has moved in the unit of meters, but distance is a scalar, having magnitude only, while displacement, being a vector, tells us in what direction. Seems kind of nitpicky to have two words defined like this. Why bother? Well, distance and displacement can actually lead to different measurements. Let's suppose we observe this snail for a few minutes and we notice that it travels in this path, 40 centimeters to the right and 30 centimeters down. How do we figure out the distance? Well, we would have to add up each little piece of the snail's motion. 40 centimeters plus 30 centimeters equals 70 centimeters. Since directions isn't a factor, I don't really have to think too hard about solving for distance. What about displacement? How far and where did it go? Displacement is 40 centimeters right and 30 centimeters down. Remember we can draw vectors with an arrow? Isn't this the same though as the snail going from here to here? Yeah, so we can say that the displacement is 40 centimeters right and 30 centimeters down, or we can say that the displacement is this length across right and down. It's essentially where you start to where you end. In other words, your overall change in position. Notice how little regard displacement has for the actual path the snail takes. The snail could have traveled a longer distance moving in circles, like this. But if the initial and the final positions remain the same, the snail's displacement would also be the same. In any case, let's see if we can figure out this displacement. Since these two motions are in different directions, we can't just add them up like we did for distance. We have to account for the fact that they are in different directions. In fact, the two displacements happen to be perpendicular, and the overall displacement connects the start to the end. This sort of looks familiar, don't you think? Isn't that a right triangle? If that's a right triangle, then that overall length is the hypotenuse. That means I can use Pythagorean's theorem. Yes, your math teacher has a purpose in your life. The sides are 40 and 30, so that would be our a and b variable. Remember, it doesn't matter what order they're in because 1 plus 2 is the same as 2 plus 1. The hypotenuse is always c. Let's plug these numbers in. Remember to square first and then add, and to get c alone, we need to square root both sides. c is 50. Since our displacements here were measured in centimeters, our overall displacement would be 2. Great! One more thing. Notice that the 40 centimeters right and the 30 centimeters down made up the triangle. That's why we call those two values the components of a vector. They represent the horizontal and vertical parts that make up the whole vector. And what we did here to find the overall displacement by adding two perpendicular components is called vector addition. So, just to recap, our distance and displacement indicate two completely different values. Distance is how much ground you cover, and displacement is your change in position, regardless of what path you take. So, we'll have to give them two separate symbols. Distance will be easy enough. We'll call that d, and displacement, which means the change in position, we can represent change by the symbol delta, and we know position has the symbol x. So displacement is delta x. Okay, let's just test ourselves. Let's say this snail walks all the way around the garden perimeter and ends up in the same spot. What's its distance? What's its displacement? Pause the video to solve. Okay, distance is how far this guy traveled. We can just add them without worrying about the direction. Displacement is how far and in what direction. That's 40 to the right, 30 down, 40 to the left, and 30 up. But wait, 40 centimeters to the right and 40 centimeters to the left are equal and opposite values. Those two would just add up to 0. And so would the 30 centimeters up and the 30 centimeters down. That makes sense. If we were to draw our vector arrow, we would start and end in the same spot, so our arrow wouldn't have any length at all. Great. What if we don't have a right triangle? What if a bird flies like this?
When the bird flies diagonally, it's essentially moving horizontally and vertically at the same time. We can simplify this motion by separating the horizontal and the vertical motions. The bird flew to the right at first and then to the left. Let's count up how far it moved horizontally altogether. In other words, let's add up all of the horizontal components. 4 to the right plus 2 to the left equals 2 to the right. Notice I'm using a negative sign to indicate the leftward direction in my calculations. I could have easily decided to use a negative sign for the rightward direction, but out of habit, I tend to think of up and right to be positive, kind of like on a graph. This is the total horizontal displacement. Let's look at the vertical. The bird flew down both times, so let's add up all of the vertical components. 2 down plus 2 down equals 4 down in total. This is the total vertical displacement. Since we want to distinguish the horizontal and vertical displacements, we're going to use the symbol delta y instead of delta x, since y tends to represent the vertical direction, like the y-axis on a graph. Okay, so altogether, the bird moved to the right 2 and down 4. Just like before, we can find the overall displacement, or the resultant displacement, from the overall change in vertical and horizontal displacements. And because horizontal and vertical, x and y, are always perpendicular, we have a guaranteed right triangle, allowing us to use Pythagorean's theorem to solve for the resultant displacement, the hypotenuse. Great! What we did here is dissect the problem into parts. We can also see the same result by looking at the big picture. The overall displacement is always the change in position. Now, the bird started here and ended here. So the overall and resultant displacement is from start to end. We can see that this vector, this overall resultant vector, has a horizontal component of 2 to the right and vertical component of 4 down.
Well, that seems simple enough. As long as we have a grid, what if we don't? Let's say an object is displaced 20 meters at an angle of 45 degrees east of north, and again 12 meters at an angle of 70 degrees south of east. How would we find the object's overall, or resultant, displacement? Well, since there's two parts to this object's motion, finding the resultant displacement is like adding the two vectors. Each vector can be resolved into its horizontal and vertical components. Since we're intentionally using horizontal, x, and vertical, y, components, which are always perpendicular to each other, we can use our trigonometric functions of sine, cosine, and tangent to find the length of this vertical component. Now, let's see. That would be the cosine of this angle would give us the adjacent side, let's call it y1, divided by the hypotenuse, 20 meters. Solving for y1, we get 14.14 meters up. We can do the same for the y component of the second segment. This time, we need sine of 70 to get the y component. Doing this, we get y2 equals 11.28 meters down. Our overall vertical displacement is 14.14 minus 11.28, which equals 2.86 meters. Remember, we're subtracting the 11.28 because it's in the opposite direction as the 14.14 meter displacement. Let's find the horizontal components next. For our first segment, we need sine of 45, giving us a value of 14.14 meters to the right. For our second segment, we need cosine of 70, giving us a value of 4.14 meters to the right. Since both vectors are to the right, we can simply add to find our total horizontal displacement, 18.24 meters. Let's not get lost in the trigonometry here. All we're doing is changing our representation of these vectors without changing their meaning. Kind of like how we can rewrite the number 4 as 2 plus 2 and 3 plus 1, and it's still the same thing. So we started with two displacement vectors joined together. This can be rewritten as two separate vectors added together. Each vector can be rewritten as its horizontal and vertical components. And since order doesn't matter with addition, these components can be rewritten to combine like terms. The sum of these components can be rewritten joined together once again. So long as one vector leads to the next in our tip-to-tail format, we can rewrite them either way. And finally, our overall horizontal and vertical displacements can be rewritten as one resultant displacement from the start of one vector to the end of the next. With one horizontal vector and one vertical vector forming a right triangle, we can use Pythagorean's theorem to solve for the resultant displacement. To describe the exact location of this resultant displacement, we can also find the angle of this vector. In physics, we often refer to the angle by the symbol theta. You might remember from math class that we can find the angle in a right triangle using the inverse of sine, cosine, and tangent. We'll pick one at random. Tangent. Theta is equal to the inverse tangent of 2.86 divided by 18.24. Theta is 8.91 degrees. There it is. Our overall displacement is 18.46 meters at an angle of 8.91 degrees north of east. Like before, we can also see the same result in the big picture. Here's our original vectors with the components shown. The object's initial position is here, and its final position is here. The resultant can be drawn from initial to final position. Can you see the rectangle you formed, and can you see how that gives us our x and y components? Okay, so let's do a brief recap on vector addition. Parallel vectors can be added normally where opposite directions can be given a negative value. Perpendicular vectors, known as vector components, can be added using Pythagorean's theorem. Component vectors can be added in any order so long as they're aligned tip to tail. The resultant must always be drawn from the beginning of one vector to the end of the second. Finally, vectors at an angle other than 80 degrees and 90 degrees can be added in 4 steps. First, find their vector components using SOHCAHTOA. Next, add their x and y components as you would for parallel vectors. Then, find the resultant vector using Pythagorean's theorem. And finally, find the angle using inverse of SOHCAHTOA. So far, we've talked about position, an object's location, distance, how much ground is covered, and displacement, change in position. In addition to these descriptions, we can also describe how quickly an object moves. You probably know this as speed. Let's take, for instance, a friendly race between a turtle and a mouse. For this to be a fair race, they would need to travel the same distance in the race. What would you need to know to figure out which animal is a faster runner? You would need to know the time it took for the animals to travel that distance. The one that spent less time traveling the same distance is the faster one. So speed is therefore dependent on both distance and time. To maximize your speed, you'd want to maximize the distance you cover and minimize the time it takes for you to do so. That's why our equation for speed places distance in the numerator and time in the denominator. But you're already familiar with that. When you describe your speed on the highway, you say something like 65 miles per hour. That per translates to divided by in math. 65 miles divided by 1 hour, that is your speed. Okay, let's get back to the race. Let's say the mouse makes it to the finish line in 10 seconds. What's his speed? Yeah, it's just 100 meters divided by 10 seconds equals 10 meters per second. Speed would be the distance divided by time, and its units would be meters per second. Since we're using distance, a scalar quantity, to calculate the speed, that makes speed a scalar too. What if we use displacement instead of distance? Let's say our clever little turtle bets the mouse that he can get to the finish line before the mouse can make it back to the start. Doing quick calculations, the mouse decides he can win this race twice and agrees. After 10 seconds, the mouse is back at the starting line and the turtle is at the 20-meter mark. When we calculate how quickly the two animals move using displacement, we notice a very significant difference. While the turtle changes its position by only 20 meters in 20 seconds, the mouse's overall change in position is 0. in 20 seconds. What we solved for here, using displacement instead of distance, is known as velocity. And since displacement is a vector, velocity would also be a vector quantity. So even though they have the same units, speed and velocity lead to different answers. Speed utilizes distance divided by time, making it a scalar. And velocity, displacement divided by time, making it a vector. Because they are different, we can use the symbol S to represent speed and the symbol V to represent velocity. I wonder, can they be the same? Well, sure. The only difference between them is distance or displacement. So, whenever those two are the same, then the value of speed and velocity are the same. So, when can distance and displacement be equal? Remember, one is a scalar and one is a vector, and vectors consider direction. So if the object doesn't change direction, then the values for distance and displacement will be the same. And therefore, the values of speed and velocity will also be the same. Okay, we've now discussed an object's location through position, how far it's moved through distance and displacement, and how quickly the object is moving through speed and velocity. What else can an object do? Well, the object can change how quickly it's moving. In other words, we can describe an object's acceleration. Now, you've probably heard about acceleration when you hear people talk about sports cars. The Lamborghini can go from 0 to 62 miles per hour in 3 seconds. Yes, that's describing the car's acceleration. It tells us how quickly the Lamborghini can change its speed. A description such as going from 30 miles per hour to 0 miles per hour in 5 seconds would also describe an object's acceleration, because it again describes how quickly the car changes speed. In physics, our definition of acceleration refers to how quickly an object gains or loses speed, or how quickly an object changes its direction. That's right. So when a car turns a corner, even if the speed is the same, it's accelerating. That's why we more closely define acceleration as how quickly an object's velocity changes. And since acceleration is derived from the vector quantity velocity, acceleration is a vector quantity too. For now, we will focus on the changing speed part of acceleration, but later on we'll tackle the changing direction part. Oh, and for simplicity, we'll give acceleration the symbol A. Okay, let's imagine a car driving along a straight road at a constant speed. What if we turned on a strobe light and we can only see the car every second? We would end up with snapshots of the car's position every second. If we overlapped these images, we would get something like this, right? Notice how evenly spaced the car positions are. That means every second the car traveled the same distance. In other words, this diagram, a strobe photograph, shows us an object moving at constant speed. Okay, let's imagine a car gaining speed. What would that look like then? Well, if a car is gaining speed, that means every second it's getting faster. And so every second it should cover more ground. So we should expect to see the spacing between the car's positions to grow. This diagram represents an object gaining speed, or accelerating. Let's imagine that the car starts from rest, and 1 second later its speed is 5 meters per second. Another second later, its speed is 10 meters per second. And after 3 seconds, its speed is 15 meters per second. Notice how every second the car is gaining a value of 5 meters per second. That's where we get our units for acceleration. The car gains 5 meters per second every second. That's the car is accelerating at 5 meters per second, or 5 meters per second squared. Now, let's imagine a car is slowing down. Can you guess what that would look like? Absolutely. If the car is slowing down, that means every second it's covering less and less distance. So, we should expect the spacing between car positions to decrease. Let's imagine that the car starts at a velocity of 10 meters per second. After 1 second, its speed is 8 meters per second. After another second, it's 6 meters per second. And finally, after 3 seconds, its speed is 4 meters per second. Every second, the car is losing 2 meters per second of speed. Our acceleration here is 2 meters per second, or again, 2 meters per second squared. Since the car is losing speed instead of gaining speed, we say that it is accelerating in the direction opposite to its velocity. If the velocity is positive, like in this example, the acceleration comes out negative when the car slows down. Be careful! A negative acceleration does not always mean that the car is slowing down. Direction, the sign of a number, is completely relative. Let's say the car is moving in the opposite direction, to the left. If the car is slowing down, the car's speed should be decreasing from 10 to 8 to 6 to 4. Like we said before, when we deal with mathematics, we use positive and negatives to tell us about direction. So, let's say that the leftward direction is the negative direction. Let's figure out the acceleration. What number can I use to go from negative 10 to negative 8? Well, that would be a plus 2. And again, from negative 8 to negative 6, from negative 6 to negative 4, we need to add the value of 2. In this case, acceleration is a positive value while velocity is a negative value. As they are in opposite directions, I know the object is slowing down. If that's true, then when an object is gaining speed, the velocity and acceleration are in the same direction. Let's try this again with the same car moving to the left, speeding up from rest. If it's gaining speed, the magnitude of the number gets larger. 0, 5, 10, and 15 meters per second. And just like before, if the object is moving to the left, we can say all of these values are negative in direction. Let's figure out the acceleration. To go from 0 to negative 5, from negative 5 to negative 10, from negative 10 to negative 15, we need to subtract a value of 5.
The acceleration is negative, and so is the velocity.
As they are in the same direction, they're both negative, we know that the object is speeding up. So there you have it. Acceleration with the symbol A tells us how quickly an object's velocity changes. We can calculate it by essentially finding the change in velocity, delta V, and dividing that by the time it takes to make that change. Its units are in meters per second, or meters per second squared. And finally, since it's a vector, it has direction that, when considered with velocity's direction, would tell us if the object is speeding up or slowing down. Well, that brings us to the end of this lesson on expressing motion through physics vocabulary. By now, you should have a good understanding of how to describe motion through an object's position, distance, displacement, speed, velocity, and acceleration, and how to determine their values through scalar and vector addition. I look forward to our next lesson where we continue expressing motion graphically. See you later on Penguin Physics.